And I always like to introduce our hometown like I'm saying, Vienna is the capital of fatty foods, classical architecture, and beautiful women. And yeah, sometimes you're not that lucky. So, what do I do otherwise? I work at Elastic. I'm working in the infrastructure team, and I'm always saying like I work in the infrastructure team, and this is a pipe. So I then pipe what I do in infrastructure into developer advocacy. So I'm out on lots of conferences doing talks. Yeah, and if I'm not doing those two things, I'm running meetups, one about databases and one about papers, so it's more on the theoretical side. So I'm trying to stay engaged with the community in Vienna. So let's jump into it. Who uses databases? I guess pretty much everybody. It's a good start. Who uses full text search already? A few. Okay, what are you using? Elasticsearch, anybody? Solar? Nobody Solar? Anything else? Lucene? Plain Lucene? Okay. Interesting. But yeah, that totally relates to the talk. We'll see why in a minute. So generally, I try to start off by explaining what is the difference between databases and full text search, and I always use this picture. Up here, you kind of have databases, and this is full text search. Like databases are very much black and white. Like you store something, and then you want to have an exact match. So either it's a yes or a no, you find something or you don't find something, and it's really just black and white of what you find and get. Whereas full text search has these shades of gray where you can see a bit more than just in the black and white version, where you actually have different shades and where you can find good matches, a bit worse matches, probably bad matches as well, but it sees in different shades and not just this very much black and white exact match or no match at all. And then people come and always say, or somebody in the audience normally comes and says like, but I can do something like select from my table where my text like percentage, for example, if I search for blue somewhere in a string, percentage blue percentage. And yes, you totally can do that, but you probably don't want to do that. Yeah, even Batman will tell you it's a double no, and we'll explain why it's a double no. First off, speed. I assume everybody has kind of an understanding how indexes work in relational databases, or at least the most common index type in databases is a B-tree, where you have a tree-like structure, and you have basically always, you jump into one of the parts or one of the leaves of the tree, so you have very few comparison operations until you find something. You can pretty much compare it to a phone book or any index you have in a book where you have terms and then you can simply look up the terms, and since they're ordered, that works well. So if you have the phone book and you search for the last name and that is what you want, then you can search easily. But if you search for the first name, for example, which would be our percentage example from SQL, from the code I've shown you, that doesn't help you at all. Like to find by first name, you will need to go through all the entries in the phone book, and the sorted nature, sorted by last name, doesn't give you anything. And exactly the same thing is true for the B tree with the percentage, whatever. If you have a wildcard at the beginning, the B tree doesn't help you at all. You will need to do a full table scan. And if you have just very few entries, it's probably fine. But okay, wait, there's...
Yeah, but it's
Okay, yeah, it will die. It's blinking, it's dying soon. I'll just shout out louder. Thank you. So stuff like that is not available in a relational database, but this is what full text search wants to do. So also feature-wise, so both performance and features is not what a relational database can give you, and they're just not built for that. It's kind of a trade-off. Databases do different things better than full text search and vice versa. So how is stuff actually stored in full text search? We have multiple steps to run. Like in a relational database or also a NoSQL database, it's pretty much you get something in, you store it on disk, and you serve it out. For full text search, you do quite a lot of work up front once you store the data. Normally, this process is called indexing, and while indexing in relational databases is normally creating a B-tree index, or this is also common in many NoSQL databases, indexing in full text search normally means taking whatever input you have, then kind of processing it and storing it in the right format, so then you can do full text search later on without any hassle. So the first thing normally you want to do is, if there is formatting like HTML tags, strip out the HTML tags, because you don't really need them for full text search. Second thing is tokenization. You have one shorter or longer string, and you want to get the actual token. So the tokens are the individual terms or words, and you want to split them up. Normally what you will do is you will split up on spaces or any punctuation marks. Depending on the algorithm, stuff like dashes are just removed and the words are combined into one. So you find the borders between the different words, you split by them, and then you just have the individual words you're looking for, or you will insert into your index. It's just like splitting stuff into the individual words. Next up, normally you will remove stop words. Stop words are very common words that appear in every text, so they add very little meaning if you search for them, but they will blow up the index you're creating here. So you will just purge them. You take out these words. This is stuff like A, as, the, but also if. This is of course implementation specific, but this is actually, there are multiple approaches, but there is a default in Lucene, and you can also provide normally your own stop word list. So if you're working in a specific domain and you know there are specific words I'm not interested in, you can simply define your own words. I just want to get rid of these and I want to keep everything else. Next up is stemming. Just like stop words are language specific, which is kind of obvious, stemming is language specific as well. Stemming tries to reduce words to their root. So it's just like cutting off the ending, or just finding one kind of normalized form of a word, because normally you're not interested when you search. Is it the singular form? Is it the plural form? Is it some flexion or whatever? I'm just interested in the concept or what I'm searching for. So stemming tries to remove the word to its word stem, kind of the root, and just strips off the ending normally. For example, in plurals, it will just throw away the endings. And of course, there are many implementations. One widely used one is called Snowball, from Snowball stem. That's what we'll use in our example as well. So this is just reducing the word to its word stem then. And optionally, you can provide synonyms. So depending on what your domain you're in, or what kind of text you're working on, you might be able to define, or you might need some synonyms where you search for one form of the word, but you want also to find other terms, and then you can provide these synonyms. And we'll actually try this out. Since I'm working for Elastic, the company providing Elasticsearch, we'll use that for our examples. And just to avoid the confusion, what is Apache Lucene? Or also, since one of us is using Apache Lucene in its plain form and Elasticsearch, Apache Lucene is actually the library. This does all of the work I've just described. And Elasticsearch is kind of the server component around it. So it does stuff like replication, sharding of your data. It provides the server component, so you have a REST interface. It provides a query DSL. All of that is part of Elasticsearch, but it kind of translates all of that into Lucene. So inside Elasticsearch, there is always Lucene running, and Lucene is actually storing the data and doing all the search work. It's kind of just hidden behind the Elasticsearch interface. But if you're using Apache Solr, which is also based on Lucene, the query DSL is different, but otherwise how it's working in the background is more or less the same. And if you're using plain Lucene, this is also totally applicable what I'm showing to you. Yeah. And even though the name kind of applies, since Apache Lucene and Solr are in the same repository and are done by the same people, actually most of the Lucene commits, if I'm not mistaken, are coming from Elastic by now because we have just more resources. So the example string we want to use is the 2 lazy dogs were slower than the less lazy dog Rover. This is the thing we want to index. And now we'll just walk through all the steps, what is happening. So the first thing we want is to remove the formatting. So we'll simply HTML strip, which we call a character filter, but it doesn't really matter. So we just strip out the HTML and are left with the plain text. Easy. Next off, we use a tokenizer. Here again, I've implied this with the multiple spaces. We just strip out all the punctuation marks and split on them, and also spaces. So we get this list of words. So the 2 lazy dogs, each of these words is just like an independent token now, run through the tokenizer. Next up, we'll just lowercase, because in most search examples, you don't really care for the upper and lower casing. You can keep it if it makes a difference for your use case, but by default, you will try to get rid of upper and lowercase, because most people will just type in a lowercase query, and you don't really care for that too much. Then we remove the stop words. So if you compare these two, we had the 2 lazy dogs. If I run it through the stop word list, 2 lazy dogs, because the, for example, is just removed. So if you run that through the stop word list, this is what remains. And then we tokenize it with Snowball, and you can see 2 lazy dogs actually becomes 2 lazy with an I at the end. That is not a typo. That is how the stemming works here. And dogs, the plural is stemmed to dog, the singular. And this is what you get. For example, if you have in your text laziness, I assume it will be stripped down to lazy in this form as well. This is just like removing it down to the root of the word. This specific implementation is Snowball, but all the others work in a similar fashion. Yes?
The Snowball method, is that internationalized? Or is
It provides lots of languages, and actually the language support. So if the question often comes up like, how does this work in Elasticsearch? How do I get my language in if it is not supported at the moment? So the thing is, first you need to add it to Lucene, because all of that is in Lucene. Then Lucene does a release. Then Elasticsearch uses the Lucene release and does an Elasticsearch release, and only then can you actually use it. But it is all in Lucene, and there you have different languages, and like the common languages are all supported. I think with Eastern European languages, some of them are missing. I was in Slovenia, and I think they have no support for Slovenian or Slovakia. But other languages are supported. And one other thing, in the further Eastern Europe, like Russian and Ukrainian, stemming is somehow, I don't really know this language, is much more complicated than in English. Like in English, it's pretty easy to just cut off the plural and have this root of the word. But in other languages, this is much harder, and they have like, this is also like a trade-off. You have either a huge list with the stemming rules, which is bad for the performance. So you have like quality over performance is a trade-off you need to make, and there is in the latest Lucene release 6.2, which came out like 2 weeks ago, they have made a new morphological language support for Ukrainian, for example. Because this was a problem. It was just not working as well as like Western European languages. So this is totally dependent on the language and how well it is supported and how complex it is depending on the language as well. I mean, there's definitely simplified Chinese. I think there is simplified Chinese. Okay. Sorry? But don't they have a representation in Latin characters then as well? I'm not sure. I have never. That's maybe it's based on the phonetics search then. But I honestly have never tried that.
Maybe we are getting into a corner of the tab.
Yeah, we're getting into a corner. Yeah, I have no idea about yeah, other languages. I have been to the Ukraine, where it is a common language problem, so I know how that works. I'm not sure about Chinese. We can probably look it up afterwards in the list of supported.
Principal question. Does that mean? Does it only? Is it always about removing things from the right end and back end, or do you sometimes remove from one?
Hmm.
Some prefixes are maybe.
Um, I mean, I'm not aware of anything, but yeah, it's yeah, probably in the Slavic language. I don't know, but this is very deep down in the Lucene stack. Then again, it's we can find it out, but it's like I'm. Yeah, we can try it out afterwards if you're interested in. But this is like getting pretty low down. I'm focusing on English today. So how you can actually run this is, I'll just jump over to, is that big enough for you to read? I guess so. This is Elasticsearch. This is actually Kibana, what you see, the visualization tool we have. And we have something called console. This here is console. And there you can run queries against it. It's basically the same as curl. It has just like some syntax highlighting, and you don't need to provide curl and X, and you don't need to provide the server and port and stuff like that. You can simply run it. So what I have here is an alpha version of 5.0 that will come out later this year, and this is actually based on Lucene 6.1. The next, I think, beta version is already coming as the next release. That will include Lucene 6.2 already. So we're working on that. So what I have here as an example, we have, if you run a string against underscore analyze, it will actually show you what it is doing in this analyze phase. It is not storing anything in Elasticsearch yet. It's just throwing that string against Elasticsearch with these character filters and tokenizers and filters I have defined, and showing you what actually happens in the background. So I'm doing just what I've shown you: HTML strip, lowercase, stop word, snowball, and tokenizer standard. This is my text with the rover text. And if I run that, you can then see this is actually what Lucene gets out of that. So you have the token, D is stripped out, which would be at position 0. So at position 1 we have 2, and it's an alphanumeric character from 4 to 7. Then we have lazy, which is at the second position with this offset, etc. So this is what Lucene is actually calculating in the background.
Will you have dog 2 times?
Yes, you will have dog 2 times. Lazy, here it is the second time. Yeah, that is what you get. So what do you assume? These dogs are fast. If we run it through the same configuration of HTML strip, etc., which words remain? Dogs fast? Okay, it's just one way to find out, and you're correct. We have dog and fast, and that's it. And the rest is stripped out. Yeah, so since we now want to actually store it in Elasticsearch, I'm just clarifying 3 terms really quickly. Think of an index like a database in a relational world. It's just a container holding your data. A type is, yeah, there's no real match for that. It's just like within an index you have just some kind of classification, like you can store different types of document, and you can just say a type is, I don't know, we have, if the index was animals, we could have a type of mammals, and I don't know, sea creatures would not be another type. You have just some kind of distinction there. And what would be a schema is called a mapping. And while you don't need to provide the mapping by default because there is an auto mapping, it is normally a good idea, at least for production environments, to provide the mapping yourself. There again, you can define, like, do I want to use HTML strip? Which tokenizers do I use? What else am I doing? And like as what kind of thing am I storing my result. So I'm just setting this up really quickly. Don't worry too much about the syntax. I'm creating my index. I'm just calling it my index. I'm simply making a put request and then say I create a synonym filter, which I have called my synonym filter. We'll reference that name in the next slide. And then I say what I want to do is, if I want to find quick, I also want this to be found via the term fast. And if somebody searches for sleepy, there is no sleepy in my text. I also want them to find it because that will be lazy in my text. So these are just synonyms I'm defining here. Next up, I'm using the analyzer I've just shown you in the previous example, and the last step I'm adding my synonyms. But again, we have HTML strip, a standard tokenizer, lowercase, stop words, snowball, and our synonyms. So this is how I set up my index. This is how I want stuff to be treated when I insert it. And then in the end, I say I have a property called, or a field, my title, that should be of the type text. And I want it to be analyzed with the analyzer I've set up on the previous slide. So here I'm using my synonym filter from the first slide. This analyzer I've called here my analyzer, and I'm just referencing that and say my analyzer and just putting all the three elements together. So this is just like one single request, but I've split it over 3 slides so you can actually read it. And then I insert 2 documents. Once we've seen both the 2 lazy dogs, and these dogs are fast. And what you will then, kind of behind the scenes, you don't really see that, is you have the inverted index. So you have the stemmed words on the one side, and then you know, okay, dog, for example, appeared 2 times in the text with the ID 1. So here I said ID, index, type, ID. This is the ID I've referenced here. So dog appears 2 times in the first document at position 3 and 10, and it appears once in document 2 at position 1. And for example, fast doesn't appear in the first document, but only in the second one and the position. Why we need the number, we will see later on. The position is helpful if you want to search for phrases. Like you say, the first word must be, I don't know, fast and dog or whatever, and then it will find just stuff that is right next after each other, so that's why the position is relevant. And then you can actually search the stuff. So this is how a search query looks like, but let's quickly do that live. I'll just insert my mapping. You can actually test your mapping if you run against your index and underscore analyze, and then you should get exactly the same result as you have before. And if you've configured it correctly, yes, that is what you're getting. And then I'm simply inserting my 2 documents. So document 1 inserted, document 2 inserted, and then I can just search it. So what I have here is I'm just saying I have a query, I want to match on the title field, and I want to search for fast. And then you have some meta information like it didn't time out, it took 3 milliseconds to search on my laptop here. For fast, I have 1 hit. This is the score. We'll dive into the score in just a minute. And it was from my index and my type. Document ID 2 had found something, and the original document that's the source was these dogs are fast. So this is how you actually find it and where you find it. And if I would want to search for quick, for example, I would still find something. And here you can see I have searched for quick, and then I find these dogs are fast because of the synonym. Yeah, we've seen those. We've searched for quick. And the other thing I promised was fuzzy search. So we can just say fuzziness auto. If you mistype, for example, I don't know how to spell rover with an A instead of the E, I still want to find stuff. If we run that query, based on our 2 documents, it will still find dog rover, even though we have just spelled it as rover. And of course, you could do that with SQL as well, but that's probably not much fun if you need to write queries like that. Okay, And the other thing we've left out so far is the scoring. Base idea is it's called term frequency, inverse document frequency, TF, IDF. All I'm saying here now will cover just searching for a single term. We'll get into searching for multiple terms in the query in a few moments. Just keep in mind we're just searching for one term, and this is the score we are calculating. So first thing is term frequency. Basic idea is the more often a word appears in one text, the more relevant that document is. For example, we had the word dog twice in the first string. So if I search for dog, the first document is probably more relevant since dog appears twice in the text, whereas in the second text, dog appears only once. That is the whole idea of the term frequency. So you take the square root of the frequency, and that is like one of the main factors contributing to it. So that looks like that. That's TF-IDF. This is how the value is calculated. In the version 5, we're switching actually TF-IDF to BM25, which is a bit more complicated. But like the approach is totally the same. It's just the values will change slightly. And you see the number of times the term appears influences the score less. So with TF-IDF, if a term appears 20 times, it's much more relevant than in BM25. BM25 kind of caps that factor. So there have been huge test sets and people have tried it out, and BM25 kind of performs better, but the general idea is still the same. The more often a term appears in a document, the more relevant that term is. Secondly, the inverse document frequency. Here the idea is a term that appears lots of time is probably not as relevant as a term that appears just a few times. So if we have the term dog, which appears 3 times in our whole in our 2 documents, this is less relevant than, for example, if I search for rover, because rover just appears a single time. And this is the 1 plus the logarithm of the number of documents divided by the document frequency plus 1, which, basically looks like that. If the term just appears a single time, it is highly relevant. The more often it appears, the less relevant it gets. And again, BM25 kind of tuned the exact numbers a bit, but the approach is totally the same. It's just like the more often the term appears, the less relevant it is. And then we have the field length norm, which is 1 divided by the square root of the number of terms, which basically means the shorter a field is, the more relevant it is. Think of it like you have a subject line and a long text body. The short subject line, if your term appears in the subject line, is probably more relevant than in the very long body of the document. So it's just assuming that shorter text, if your search term appears in the shorter text, this is more relevant than if it's a very long text and the content is appearing there. If you're interested in the finer details of BM25, we've done talks just on that, but that gets pretty deep down into math formulas, and we'll skip that for today, I guess. So what I want to show you is I can actually display how this works. So if I run a question mark explain against my query, I can see, okay, I have 2 total hits, and they have different scores. So here, first, the 2 lazy dogs appear first, and they have a score of 0.39 something, and the other document has a value of 0.30 something. And this is pretty small. So you can actually see here how the number is calculated and all the factors that contribute to that actually. The gist of it is basically the first document is ranked higher because dogs appear 2 times, which is kind of totally in the favor of the first document. The second document has the slight advantage that the text is shorter. But that the term is appearing twice instead of 1 time is giving it a bigger improvement over the shorter text. And other than that, the formulas have been tried out on big texts, and this is kind of what people kind of expect when they do full text search. BM25 slightly changes the parameters, but this is what you get, like number of terms, how many or how often does my term appear in the document is relevant, but also the text length and like how often the term I'm searching for appears in the document overall. Yes?
Are the synonyms applied at the index time or the search time? Can you change the synonyms?
If I'm not mistaken, both approaches are possible. Like I think, like this is, I'm just thinking how this is actually stored in Lucene. I think there are generally two approaches how you can store synonyms. I think one is at insert time and one is at lookup time, which is kind of a trade-off between space and, because like if you store the synonyms, you will duplicate the space obviously, or you need multiple hits. Otherwise, it's just a runtime overhead if you need to, because you need to search for multiple terms then at runtime. Either you duplicate to have more disk space and data in memory, or you need to run multiple actual search terms. I think this is how that's implemented deep down. Yeah, these were the scores, and on the slide it's probably easy to read. And you see, for example, the first document with the highest score. There we had the frequency, the term dog appeared twice in that document. So this was the higher value, and this was the main contributing factor to the higher count. Now, when we search for more than one term, stuff gets a little more complicated, but it's also very nice to show. It's called the vector space model. If you search for multiple terms, each of them is searched independently, and each of them is scored independently. And then, let's assume we're searching for two terms, we get a two-dimensional space. Each of those terms is a space. And then you can actually see which of your terms is closest to what you have been searching for. So I guess it's easiest when I just show you an example. So assume you are searching for dog and rover. And since we're searching for two terms, we're in two-dimensional space, it's very easy to draw. One axis is dog, and one axis is rover. And I've made up hypothetical values now, and I've assumed rover has a much higher importance because rover is probably appears just a very few times in my document body, whereas dog appears probably more often. So dog has just a weight of 1, whereas rover has a weight of 5, because rover is much less common. How close it is to, if a document just contains dog, how close it is to my actual dog-rover vector, and if a document just contains rover, how close is that to my dog-rover vector. So you can see if a document only contains rover, it's much closer to my dog-rover. Close it is to, if a document just contains dog, how close it is to my actual dog-rover vector, and if a document just contains rover, how close is that to my dog-rover vector. So you can see if a document only contains rover, it's much closer to my dog-rover perfect match than if a document just contains dog. And of course, with 2 dimensions, we can very easily imagine that if we have 3, 4, 5, whatever terms, you get more dimensions, and it's not as easy to imagine, but like the approach is the same. You just calculate like how distant are the different terms to the perfect match, and where do I have that in my vector space model. Okay, so to conclude, stuff you need to do for indexing. This is what happens when you store the actual data. This is also why stuff in full text search normally is not available immediately after inserting. We normally call it like near real time, which is also kind of different to the expectation you have from a relational database or a NoSQL database. There you just throw stuff at the database and expect it like 1 millisecond after sending off my query, and I've got the response, yes, stuff was inserted. I expect to get the data back when I query it. In Elasticsearch, this is not really the case because A, we need to do some indexing overhead. On the other hand, storing data is handled a little differently, like kind of data is immutable, so we only write batches by default at once a second. So it will take some very minor delay between actually writing data and it being available for reads. Even though you can force stuff to be the option is called refresh. You can actually force Elasticsearch to actually write stuff, and your query will get the latest data. So for indexing, what you need to do is, first off, throw out the formatting. Next, cut the different words into the tokens you want to search. And then you normally will just lowercase them. You don't care for the casing. You remove the stop words, which add very little meaning, but would just blow up your index. You remove them to the word stem. And optionally, you can, at the end, add your synonyms. Yes?
Is there a way of detecting the language of the content? Because in Denmark, we often have documents or text that are both in Danish or English. Is there a kind of filter you can put in between to detect the language?
I don't think there is, like, you can set up so for different languages you will need to use different indexes or different types probably. There is no auto detection. Also, like, this would probably be a bit faulty. Like, if it doesn't properly detect it, all your analyzation will go to hell. So you need to explicitly provide that that's like not auto detected or anything. Like, normally you should know what language the stuff is coming from, right? Okay, or if you don't, then you will need to find another system that actually finds it out. But that is actually its own probably very complicated problem to correctly guess the language.
And it could be a mix.
Or it could be, yeah. No, we don't have any heuristics or anything just to guess the language and then actually do the right thing. No, this is no. Yes.
But what if you have localized data so that you have multiple texts per document? Say that you have a property in your document that you have both in Danish and in English.
Yeah, sure. Then you need different fields with different settings. Like we have defined the synonyms and everything, and then we've just set that for one specific field. Like, so for example, in this example, when I set up, I have my synonyms and my blah, and I could define, in the analyzer, I could define my language and everything. And then I've said this, my analyzer I've defined here is just going for the attribute my title. Sorry, once again? With more than one doc? Ah, you mean you need three occurrences of dog?
I wonder, this one is not like serial. It doesn't really understand it.
No, it's not a natural language processor or anything that really understands like the structure of the text. This is just tokenizing and then working on the words independently. So I'm just thinking. I mean, of course, the score will be influenced. I'm not sure if we need to look it up in the API document if you can define it multiple times. What you can do is, what is also different to relational databases is you can have must criteria or must not criteria and should, where you could, for example, say, I have 3 different terms which should appear, and if all of them appear, they are ranked the highest. But only then you can set a threshold, for example, and say, but of these 3 terms, at least 2 must appear. But like saying that dogs must appear at least 3 times, yeah, we'll have a look. Maybe the API can do it, but yeah, we don't really understand the language. We pass it the words and then search for the words you provide. And this tries to find stuff, but it's not really understanding your content, or it's not really understanding your language or anything. It's just like you configure the specific rules, and then you will just try to find stuff based on those rules. So it's probably less clever than you would expect it to be. It's just like, it is a simple model in the background. It doesn't need all the all these heuristics or anything. It's very deterministic actually. Yes.
How about alternative spellings like in Danish, K and C can in some cases be
I mean, you can of course try out the fuzziness. Like fuzziness, I think the base model of fuzziness originally is based on the Levenstein distance, but it has, I think, been refined in how we use it now. Normally, like what the fuzziness, what you want is like either there is a letter missing, or there's a letter too much, or like a letter is wrong, and then you can kind of tune this distance, like how many wrong or missing or too many letters should be allowed, like 1, 2, 3. But this will depend on your use case and how this is like a tuning parameter you need to find for your domain. Like some domains are pretty strict because they already find lots of stuff. Others need to be a bit more lenient and then try to find lots of different stuff if you don't have anything that matches. Also, you could normally run like exact or no fuzziness, and if you don't get any results, you run another query with fuzziness and then increase the fuzziness if you don't find anything. So you could probably do this in an iterative fashion just to find.
now you have tokenized. In English they would spell it with an S, in American with a
Yeah, but that's probably even cut out by this by the stemming, depending on the word. Maybe that's not depending on the word. It's not even like in the final result.
We have something like Cuba and Copenhagen and Canada. They all will see, but we actually express them with K. And we have same yes, sometimes zero is yes, but it's C in the language. It says there are sweet are they in there?
You mean like a phonetic search?
Yeah. These rules are common to all European languages.
So, at least in German, we don't really have that. Also in English, I'm not really aware.
City.
Oh,
Say city.
okay.
You express an S, but you spell it with a C.
but you search like you spell it right, so wouldn't do your searching from now on.
Like at least not in the default. There is no phonetic matching by default.
Like a name like Eric, would you spell with
C or a K.
I think that Lucene doesn't provide that, but there are other technical libraries that
Yeah. I mean, fuzziness will get you a long way with that, but I'm not sure if there is. I'm not at least I'm not aware of any specific rules that are applied to fix that up.
Some of these examples could be fixed using synonyms. Like
Of course.
search street names, some of them have multiple spellings and multiple.
Of course, but you probably get huge synonym lists, which is also kind of a performance issue afterwards. You probably don't want to do that, and it would be more clever if it's like a general rule, if you could apply that before. But I'm not really sure. Like phonetic matching is. I'm not aware of any phonetic matching right now, or at least we don't really need it in German, and I've never used it in English. Sorry?
was die Straßen? Die Straße? Ich glaube, Doppel S ist I.
You mean the letter? Yeah, that will depend on how you actually tokenize stuff, but you probably just for the search index you will probably just replace this special letter with a double S, and like the umlauts in German you will probably just flatten them out to a, for example, to AE, and you just probably flatten it out to ASCII characters, which is then, and of course when you search for something, the search terms run through the same analyzer and the same process. This is why once you have indexed something, you cannot simply switch on the fly how you analyze stuff, because everything has. everything has been stored in a specific way, and you will only get proper results if your search queries actually run through the exactly same process. So you would need to re-index all the data if you want to change that. Sure, you can do all of that, or you simply, we have a reindex API where you simply say, okay, my mapping is now different, and since I have the source, the original document still there, I can simply just reindex, and it's a background process, and then you can just point to the new index. There is a phonetic, okay. Ah, nice. I'm not even aware of the rules. Interesting, okay. Yeah, and we've talked about the scoring. Term frequency, like the more often the term appears, the more relevant that document is. Inverse document frequency, the less frequent a term is overall your documents, the more relevant it is. Field length norm, shorter fields are more relevant than longer fields. And, bless you, the vector space model, you have just the space, depending on how many terms you have that many dimensions, and then you can actually calculate how close is what I have in different documents to the perfect match. Okay. We've already had quite some questions, more questions. Yes.
I've been playing around with full text search and took the characteristics of the house, as you built here, and renovation here, and tried to find all the houses built in a given year. But I got a match if I had a house that was built but renovated in the year 5. Is there any proximity scoring? So they giving the build year and the build, the year, the word build and the year is closer as better scoring than if they're in opposite side.
Yes, you should be able to do that. But you don't have the information like explicit. It's just like within the regular text. You cannot extract the.
Yeah, well, if you have the example, you have your text example, you have
Yeah, you can search either for phrases or like stuff needs to be closer together. Yeah, you can configure stuff like that. For example, phrases is just like this word after that word. You can define stuff like that. Also proximity, or like we've kind of skipped it. We have just focused on the full text search aspect so far. But there are also like filters in Elasticsearch, which is what databases do. It's just like black-white constraint, like yes, this needs to happen. So if you can extract that content, you don't actually need to use full text search. But if you can extract the facts like this has been built in this year and this has been renovated in that year, you can just filter on that, and this is kind of the step before going down to full text search, and this is just like excluding documents based on these hard constraint rules. Okay, thank you.